Hi everyone, I'm Jill Raleigh and this is my Lab 5, Faraday's Law, and I'm in Lab XL11. For an introduction, today we're dropping magnets into a conducive aluminum tube. This help us better understand the curly electric fields that are the product of bar magnets, and because the aluminum is not explicitly magnetic, it's actually going to allow the magnet to fall all the way down. Some key topics that we visit today from Physics 2212 would be Faraday's Law, determining that change in the magnetic flux throughout the experiment, the Biot-Savart law, determining the force exerted on the ring by the magnet, and Newton's second and third laws. These are going to help us understand the total net force on the magnet as it's falling. So some data. Tube length was 0.3 meters, inner radius 0.015 meters, total radius 0.35 meters. The aluminum width was 0.02 meters, and the mu was from lab 3. I had used 3.5 meters squared. With my trials, I averaged in around 1.256 seconds on average to fall. But then when I use the closed script model, you can see here the velocity versus time graph and the end screenshot of my bar magnet falling. So the tube was created, the tube's time in seconds was around 3.372 seconds. So obviously a significant difference. Some highlights from the closed script code. D flux I calculated here. I wanted to point out the parts where I edited the closed script code itself. You can see that I also determined magnetic field here to the dipole. And then in terms of B field, I also edited this here to include the ring measurements. And then with the current ring, I edited this last part to match. So to interpret the simulation, you're looking at it from above, and the red and blue indicates current flowing in opposite directions. What color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? I found that the red corresponds to deflux UT, as it's labeled that way in the closed script code. This would be the counterclockwise direction, and the blue would be the clockwise direction. What happens to the dynamic of the system when you flip the magnet around? The magnet is falling north. So because it's not the north end of the magnet anymore, it's the south, the system will not accelerate as quickly because the gravitational pull is not the same on the magnet. Then how does the total time in tube of the real world system compare to that of a computational system? How might the computational system be made more accurate? My average time in the system was much longer in the simulation from closed script. This is likely due to the mu value I calculated in lab 3, which may be imperfect. And then what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So back here again, you're going to see that a constant velocity in the middle is maintained. So that means that there's no acceleration. And then there's a deceleration here and a deceleration here and then an acceleration. So from this graph, you can surmise that the net force accelerates in the beginning, 0 in the middle for constant velocity, and decelerates at the end. Some follow-up questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics change? The magnet would actually fall slower because there's less strength in the attraction between the magnet and the tube now. And if there were holes or slots cut in the tube, this would actually affect the ring because the magnet's now falling faster because there is less attraction between the tube and the magnet due to those gaps. Thank you for following along, and I hope you have a great night.